Wonderful.
Okay. Okay, so good morning again. Let me share my screen first of all. Okay. Okay, so good morning again. So everybody in the group, including Janaya, they are familiar with me. I'm a professor at the Department of Mathematics and Statistics, and this talk is about applications of mathematics to nuclear engineering. And I also want to mention the number of students I worked with over the last few years. Many of these students graduated, some found jobs, some are actually in graduate school. And currently I have 3 students working with me. So that's Alina Ali, Rafael Galvan, and Salman Khan. Okay, so just a brief introduction. What is the nuclear science? Nuclear science is a research field about radiation and radioactive material for the benefit of mankind. And they're using nuclear reactions to generate power. So the nuclear energy provides a significant amount of energy. For example, in the United States, the nuclear power generates about 19% of electricity. In France, it's about 90%. And the nuclear power applications involve the use of these reactions, either in large central power stations or in small mobile power plants. One of applications of nuclear power in those smaller mobile power plants is, for example, for submarines, aircrafts, spacecrafts, because the advantage of the nuclear power is that it is used to allow extended operations without the support ships that carry the traditional fuel oil. So, for example, for submarines, the nuclear power enables submarines to cruise without large amounts of oxygen, and so they can stay underwater for a very long time. Also, the aircraft carriers, they can stay without conventionally powered plants for a long time, and the space that is usually taken up by the traditional oil can be then used for other supplies. And the same thing for the spacecrafts. If a nuclear reaction is used to provide electricity, then the spacecrafts can travel long distances in deep space, which is important in explorations. And so how does the math come into the picture? Well, I put some quotes here from a famous scientist about math. One of my favorite is that mathematics is the key and the door to the sciences, by Roger Bacon from 1300s. And so from the 13th century. And so Dr. Parker works so hard to get funding for Scholars Academy to provide scholarships for students. And when she was applying for the Nuclear Regulatory Commission, she asked me to participate in this grant with a few other faculty. And so I was thinking, how can I adopt my research? How can I find some applications of math to nuclear engineering? And to be honest, it wasn't that hard. There's so many applications. And actually, there was one particular application that I can use my PhD research to produce some results. I was very happy about this, and I'm very thankful to Dr. Parker and the Scholars Academy and to all the colleagues from Scholars Academy for this opportunity to be on this grant and on all other grants, and to help our students and support their undergraduate research. And so just briefly about some branches of mathematics that are used in nuclear science. Many of our students have to take calculus, STEM majors. And so calculus is heavily used in many applications, so including nuclear engineering. And in particular from calculus, then we branch to some upper level math courses that we even have like a senior and junior courses at UHD. So for example, differential equations, analysis, differential geometry. These are some fields that are used in nuclear engineering. Then of course, algebra. In particular, linear algebra and abstract algebra that we study as math majors in our senior years. Of course, statistics and numerical methods. And when we come to numerical methods, this is a very important field in many applications of math. So when we talk about numerical methods, of course, we have to include computer science and data science, as well as important fields that are used to solve some problems. And so I just wanted to go briefly about some topics from calculus. Some of the students, Janaya took probably the calculus class before, but I was hoping there would be some students who don't have a calculus yet, haven't taken this class yet. So I would describe the definition of derivative, which is important in many applications in both STEM, but also in social sciences, in financial mathematics, and so on. So if we consider a curve, the graph of function f given by this black curve, and we fix 2 points on this graph. Okay, the first point has x coordinate a and the y coordinate f of a, and then another point slightly further away, which has the x coordinate a plus h and the y coordinate f of a plus h. And so we're interested in a secant line. This is this pink line connecting these 2 points. So this is a line just connecting 2 points on some graph. And so to find the slope of the secant line, as we study even in college algebra class in our freshman years, is basically the distance in y coordinates over the distance in x coordinates. So the distance in y coordinates is, of course, f of a plus h minus f of a. That's why this is in the numerator. And then the denominator, the distance between x coordinates, a plus h minus a. So a and a will cancel. And so that's why the denominator is just h. Because the distance, how far are these 2 points from each other along the x-axis, is just h. So this is the formula that many students, even in college algebra, learn. This is the slope of line where we know 2 points on the line. And so what we are interested in calculus, we want to let this point, the second point, slide along this curve and become very close to the first point. So the first point with coordinates a and f of a is fixed, and the second point is just sliding slowly along this black curve. And so in that case, the secant line, of course, is changing the position because we are changing this point. And so in the moment where the 2 points join and become 1 point, this pink line basically becomes this red line. And this red line has a special name. It's called the tangent line, or the tangent to the graph of this function f. And so what happens in that process is basically when we think about the slope of the secant line, what happens when these 2 points are becoming 1 point, when the second point is sliding along this graph, that means that the distance between them, between their coordinates, x coordinates, is going to 0. So that means that this h, the parameter h, denoting the distance, becomes 0. And this is what in calculus we study as limit. So the limit of the secant line is basically, the slope of the secant line is the slope of the tangent line. So this quantity f prime of 0, this symbol prime, means basically this limit when h goes to 0, and we call it, when this limit exists, we call it the derivative of this function f at the point a. So what really it means, this derivative f prime of a means the slope of the tangent line or the slope of the graph, or in other words, it means the rate of change of this function at that point a f of a. And the rate of change means whether this function is going up, whether this function is going down. So it tells us how fast this function is changing. And this is certainly important in many applications, in social sciences, in natural sciences, in engineering, and when we are interested in some quantity and how this quantity changes. So to make some connection with, not with the natural sciences, but I typically tell my students in businesses, we have some F, let's say F is the price of some article in time. So we think that the first, the independent variable X is time and F is the price of that article. So we can study what is the rate of change of the price, how the price is changing. Is it increasing or decreasing? It's very important in a business world to know the price of some articles, the price of stocks, for example, and this is all given by this derivative. So that's why the derivative is very important quantity. And that's why in Calculus 1, most of Calculus 1 is about derivatives, many formulas we study regarding derivatives, applications, and so on. And so this is one of the first topics we study in Calculus 1, and I thought it would be nice to go over it before we go into some research. And so in calculus, then we study what are the derivatives of some elementary functions. This definition using limit is kind of a complicated definition, and we show this definition in the first lecture in calculus. We find for some particular simple functions f, we use this definition, we find the derivative. But because we use these derivatives all the time, we cannot always go back to that definition and spend time finding the derivative using the limit definition. It's a long definition. Then we need to know on the top of our head derivatives of some elementary functions in math. And so even in college algebra, we study what are the elementary functions. Of course, polynomial functions. Those are some of the most elementary functions. They're of the form x to the power n. like x squared, x cubed, quadratic cubic functions. If n is a positive integer, this is a polynomial function. And so in calculus class, in our first lecture on derivatives, we get this formula, we derive this formula that the derivative of x to the n is n times x to the n minus 1. Okay, so if we should learn anything from calculus and remember anything, is the derivative of a polynomial function. And then we say that this actually formula extends not only when n is a positive integer, but n can be even a negative integer, it can be a fraction, positive, negative. So actually this formula extends to power functions. And so this number r can be any real number, what I have this in the second line. Okay, so we can have the formula x to the power r, derivative is r x to the r minus 1. So this r can be any real number. We're not restricted only to natural numbers, positive integers, but this is true for actually all real numbers. And then in calculus 1, we also introduce what are the derivatives of some trigonometric functions. We studied trigonometric functions in pre-calculus, sine function, cosine function, tangent, cotangent. So in particular, just kind of a reminder for those students who took calculus 1, derivative of sine x is cosine x, derivative of cosine x is negative sine x. And then in calculus 2, we study also what are the derivatives of exponential functions, e to the power x, as well as logarithmic functions, ln x, and so on. So these functions are the elementary functions. And if we remember those derivatives, then we are able to solve all kinds of complicated problems. So in math, we always study first simple problems, simple functions, and then we build up and we study more complicated problems. And so going back to nuclear science, I outlined here actually several projects that you can see some applications of math, and then later on I will talk about some particular projects I'm working now with my students. And so one of the projects or one of the applications of math is about radioactivity. So over 100 years ago, Henry Becquerel was working, was working with compounds which contain uranium. And he found that the plates covered to keep out light became fogged when uranium was present or near the plates. And so this fogging suggested that there was some kind of ray that passed through these plate coverings. And later on, there were other materials that were discovered to also emit those rays. And those materials are said to be radioactive, and they undergo radioactive decay. So students who are taking chemistry or chemistry majors, biology majors, they're probably familiar with this, with the radioactive decay and radioactive elements. And so a few years later, Rutherford discovered that uranium compounds actually produce 3 different kinds of radiation that were called alpha, beta, and gamma. So the alpha radiation can be stopped only by a sheet of paper. Okay, beta particles, beta radiation can be stopped by a 6 millimeters of aluminum sheet, while gamma rays can be stopped by several millimeters of lead. Okay, so this is the difference in these rays, alpha, beta, and gamma. And again, chemistry majors probably know much more about this than I do, but I thought it was interesting to mention so you can kind of connect with your what you are studying. And so how does the math theory comes into the play? Well, the fundamental law governing decay processes states what I wrote here, that the probability per unit time that the nucleus will decay is a constant. Constant meaning it's independent of time, independent of the number of those nuclei. And this constant is typically in chemistry denoted by lambda. So when we introduce some math variables here, we introduce t, variable t to stand for time, and then another function, dependent variable, n of t, denoting the number of atoms at this particular time t that have not decayed. Okay, so t is the time, and then n of t is a function of t. Is the number of atoms that haven't decayed at that particular specified time t. Then lambda, this constant we introduced earlier, times n of t is the decay rate of the activity of this radioactive element at the time t, sometimes denoted by alpha of t. And so the mathematical equation that governs the decrease of the number of undecayed nuclei or atoms at the time t is this differential equation, derivative n prime of t. So this is the rate of change. How does the number of undecayed atoms changes in time? So derivative again is the rate of change. It tells us that it's decreasing. That's why we have this negative sign. So the rate of change says that the number of atoms is decreasing, and the rate is lambda times n of t. So this is a very simple differential equation. Again, lambda is just a number. It's a constant. T is a variable, and n is a function. So this is a very simple differential equation. So we're trying to figure out which function n of t satisfies this equation. And when we study calculus, especially if you're a biology major or chemistry major, we give this as an example of application of calculus, application of derivatives. So probably you're familiar then with this equation and how to solve it. So when we have differential equations, when we want to solve them, we also need some conditions. We're interested what is the number of atoms at the time t, but we need to know what we start with. So we need to know what is the number of those atoms or nuclei at the initial time, at the time t is equal to 0. So this is something that is given like from the experiment. So we have that the number of those atoms at the beginning of our experiment, saying that the beginning of our experiment is at time t is equal to 0, is this number n with the subscript 0. So n subscript 0 is just the number that we know, the number of those atoms at the initial time at the beginning of our experiment. And so we are then interested how to find what is the number of atoms, n of t, undecayed atoms at any other time t later on in the experiment. And so that's what is governed by this differential equation, because this differential equation depends, the function n depends only on one variable. This is called ordinary differential equation. So if you're a math major or even computer science majors and I think chemistry and biology majors, you have to take the class in ordinary differential equations, which is our math class, Math 3301. And in that class, we study only ordinary differential equations. So when the dependent function, the dependent variable or the function depends only on one independent variable. We also have a class for math majors, partial differential equations, where this function depends on more than one variable. And so this is just an ordinary differential equation. And we say this is initial value problem because we have this initial condition. And so the solution of this equation can be found just by using some very elementary techniques from calculus, using integrals that you study later on at the end of calculus 1. And the solution is given by this formula. So this function tells us in advance what the number of undecayed atoms will be at any time t. And this can be confirmed by the experiment that this is really true. Basically, that this equation describes the decay of atoms in a radioactive element. And so what we see from the solution is that the solution, of course, depends on the initial number of atoms, depends on this constant lambda, E is just the base of the natural logarithm. So this is the exponential function where t is a variable. So for any particular time t, let's say we want to see what is the number of undecayed atoms 1 hour after our experiment. We just have to plug time t on the right-hand side at the time t is 1 hour. N0 is the initial number of undecayed atoms. Lambda is that constant for that particular radioactive element. And then by plugging, we can find on the right-hand side what that number is. And that's the number of those undecayed atoms. And so what we see from this solution is that this is exponential function, decreasing exponential function, because in the exponent, we have a negative number, negative lambda times t. So the number of nuclei decreases exponentially. Okay, and so this is just another way of rewriting this, but I don't have to go into that. And so now going back to some more explanation about the units that the radioactive activity is measured in. Traditionally, it's measured in units of Curies, named after Marie and Pierre Curie. And 1 Curie is 3.7 times 10 to the 10 decays per second. So this is a huge amount of decays, 3.7 times 10 to the 10th. So huge number of decays, and just a few words about Pierre and Marie Curie, because they're probably the most famous scientists working in radioactivity. Pierre Curie was a French scientist, French physicist, and he received the Nobel Prize in Physics with his wife, Marie Curie, and also Henri Becquerel in 1903. And Marie Curie was a Polish and naturalized French physicist, and she's the first woman to win a Nobel Prize. She's also the first person and only woman to win Nobel Prize twice, and the only person to win a Nobel Prize in 2 different sciences, actually physics and chemistry. And Curie family is very famous for Nobel Prizes. Their daughter was also a scientist, chemist. So in Curie family, they won a total of 5 Nobel Prizes. And also for Marie Curie, just to mention, she's the first woman to actually become a professor at the University of Paris. So very impressive scientists. The standard international unit of activity that is used today is becquerel, named after Henry Becquerel, and 1 becquerel is only 1 decay per second, so much less than what the Curie unit is. Henry Becquerel was a French scientist, French physicist, and also together with Marie and Pierre Curie, he received that Nobel Prize in Physics in 1903. And this is a picture from from online picture about their lab from, as you see, late 1800s. And so how is this used now in some projects that we have with students? And also you study this sometimes in calculus class. So what is important for the radioactive elements is to figure out what is the half-life. So what is the half-life? It's basically the time during which the number of atoms decreases by half. And it's denoted by T subscript 1/2. So this capital T subscript 1/2 is the half-time. So this is very important for nuclear scientists to know what is the half-time of some radioactive element they're working with. And so the half-life of this uranium is 4.5 billion years. So what that means is that when the current amount of uranium that there is on Earth, in order for this amount to decay, half of this amount to decay, we need 4.5 billion years. So it's a very slow decay process. And so how can we figure out what is this time, this half time? Well, particularly using our math notation, what it means that the number of undecayed atoms at that time is half of what we started with, half of the initial amount. So N0/2. And so how can we figure this out now? Well, using our solution of the differential equation that we have, okay, that N of T equals the initial amount times e to the minus lambda T. We just plug for T, this time T 1/2, this half time. So the left-hand side is then half of the initial amount. This is the right-hand side. And the only unknown here is this time, this capital T. Okay, so again, N0 is the initial number of atoms, which we know from the beginning of our experiment, the initial quantity. Lambda is the constant related to a particular radioactive element. And so from this equation, we just have to solve for T 1/2. And this is a very simple exponential equation because T is in the exponent. So even in college algebra, we study how to solve this kind of equation. So I have here in the last line, basically, first of all, we cancel N0 on both sides or divide by N0. We end up with this equation. And so again, T is in the exponent. So how can we reach this variable in the exponent? Well, we have to use the inverse operation for exponent, which is logarithm. Okay, so very simple. So taking the logarithm, this is ln of both sides, ln of 1/2 becomes ln of this exponential expression. But the ln and exponential are inverse, so they cancel. So that's why we have minus lambda T 1/2. So this is a kind of some application that you study in college algebra, how to solve exponential equations. And now that we have T without the exponent, then we can just divide both sides by a negative lambda. And ln 1/2 is minus ln of 2. So that's how we solve for this half time. So the half time is ln of 2, natural logarithm of number 2, divided by that constant lambda. Lambda is a constant for the particular radioactive element. And so I have a graph here that I have taken from the internet about another radioactive element, strontium 90. And so this is the graph of the decay. As we say from our differential equation, the solution is exponential function, the decaying exponential function. And this is actually from the experiment. So they started at the initial time 0. When they started working on their experiment, they had 100 grams. So this vertical axis in grams, 100 grams of this strontium. And then, as you see, after 25 years, so this was a very long experiment. After 25 years, there are only 50 grams of this initial amount. And so what is a half time here? Half time actually is 25. So every 25 years, the amount of the strontium that we start with decays by half. So we're left with half. So after 25 years, we have 50 grams. After 50 years, we have 25 grams and so on. So this is really an exponential function as we see from the math formula. Okay, and so a more complicated example of radioactive decay is when we have a radioactive atom B, which is within a chain of decay, in a decay chain. So we have this radioactive atom B, but this atom B is formed with using the decay of an atom A, and then atom B decays into C. And this chain can continue. But let's just look at these 3 particular atoms. So B is in the middle. It's formed by decaying from A, and then it this atom B decays into C. So we want to see what is the rate of change of the number of atoms B. Of course, it depends on A and it depends on C because B is formed using the decay from A, and then it itself decays into C. So a similar equation to what we had before, differential equation. Now this is the rate of change of the atoms B, depends on how they're formed from atoms A and how they decay. This is how they decay into atom C. And then the solution can be given again by now a more complicated formula because the equation is more complicated. Okay, so that's the first kind of field where mathematics is used, very elementary mathematics, as you can see. We don't have anything more advanced than calculus. So even the students who are joining the projects in nuclear science, not only with me in math, but also with Dr. Zhang in chemistry, Dr. Benavides, Dr. Weining Fang, and all other faculty involved in projects, they don't have to be senior students and have lots of background. They can be even freshman students, because the concept that we really need for the research, the faculty will teach, and so you will be able to understand the project and make some progress. And so the second type of research where math, very elementary math is used is nuclear reactions. So a few words about fundamental particles. What are the fundamental particles in physics? They're electrons, protons, neutrons, photons, neutrinos. When I was a student, when I studied physics in high school, maybe 25 years ago, the only fundamental particles at that time were electrons, protons, and neutrons. So this tells you how physics is changing, and chemistry as well. These sciences, every day there are new discoveries. So you really have to be involved and follow up these new discoveries to be involved in research. And so electrons are typically negative. They carry negative charge, but there are some recently found positive electrons. They're relatively rare. Protons are typically positive, but of course now recently some negative charged protons were found as well. However, they're very rare and they have no importance in nuclear engineering. Neutrons are not stable particles, and then there are also photons and neutrinos. And so what is a nuclear reaction? A nuclear reaction is said to have taken place when two nuclear particles interact and they produce two or more nuclear particles or gamma rays. And so just a very simple way of writing a nuclear reaction, A plus B results in C and D. Okay, so chemistry majors know this much more than me. I just know some fundamental laws that kind of math laws that describe these reactions. But if you're a chemistry major, I'm sure somewhere in your coursework you will encounter equations related to nuclear reactions. And so the fundamental mathematics law or physics law governing these reactions are conservation laws. Conservation of nucleus, conservation of charge, conservation of momentum, conservation of energy. So these are conservation laws. And so conservation of nucleus says that the total number of nucleus before the reaction and after the reaction has to be same, and so on. Like conservation of energy, the total energy before the reaction and after the reaction has to be the same. The total energy is conserved in nuclear reactions. And so, so in particular, conservation of energy can be used to predict whether a certain nuclear reaction is possible. So in advanced, with math tools, we can predict whether some reactions are possible or not. And this certainly helps the physicists and chemists who work in nuclear engineering and nuclear power plants. So how can we see whether this reaction is possible or not? Well, the total energy before the reaction and after the reaction has to be the same. And the total energy is the sum of kinetic energy and rest mass energy. So the kinetic energy is denoted by E. So for example, before the reaction, we have the kinetic energy for this radioactive element A and the kinetic energy for the radioactive element B. And then we also have rest mass energy for these two elements, which is mc squared. So the mass of A times c squared, c is the speed of light, and mbc squared. So what is on the left-hand side of this equation? This equation is basically the total energy, kinetic plus the rest mass energy before the reaction. And then on the right-hand side, we have the same kinetic energy and the rest mass energy for the elements C and D. So these two quantities have to be the same. That's why we have the equal sign here. Or in other words, this last line is just rearranging the terms. So basically moving the rest mass energy, total rest mass energy to the left-hand side, and then the kinetic energy to the right-hand side, just rearranging the terms. And so this is the same equation I have here, the first equation on the top, just rearranging the terms, which this is the conservation law stating that the total energy before and after the reaction has to be the same. And so if we just one of these sides denote by Q, it's called value of reaction. So I just chose here the left-hand side, but of course, because they're the same, the left-hand side and the right-hand side are the same, so it's the same quantity Q. And so when Q is positive, such reactions are called exothermic reactions. What it means when Q is positive, that means this quantity is positive, like the right-hand side and the left-hand side are positive. So if this quantity is positive, that means that this term is bigger than this term. So that means that the kinetic energy of C and D is bigger than the kinetic energy of A and B. So that means there is increase in kinetic energy. Also, if that quantity is positive, that means that this part is bigger than this part. Okay, so that means that the rest mass energy for elements A and B was bigger than the rest mass energy for C and D. So that means that the mass, there is a decrease in mass. And so these reactions are called exothermic reactions. So based on these energies, we can predict whether a certain reaction is possible or not. And if Q is negative, just the other way around, if Q is negative, then this means that this quantity is less than this quantity. So the energy, the kinetic energy on the right-hand side is less than the kinetic energy that was on the left-hand side of the reaction. So there is a decrease in kinetic energy and then increase in mass. And these are called endothermic reactions because the kinetic energy is converted into mass. So this is another very simple applications of math, just using algebra to figure out whether certain reactions are possible or not. Okay, and so now I want to talk a little bit about the research that is a little bit more advanced, that recently I have been working with students in the last couple of years. Just some data about the nuclear plants. There are 440 nuclear plants in the world as of January 2021, and I here have the map of the world with the plants. The US is the world's largest producer of nuclear power, accounting for more than 30% of worldwide nuclear generation of electricity. And there are 96 units in US, 96 power plants as of December 2019. So this is the latest data I was able to find on the web. And this is the map of nuclear plants in the US. So we have 2 in Texas. And so just some history, electricity was generated by a nuclear reactor for the first time in Oak Ridge in 1948. Oak Ridge is a lab in Tennessee, in United States. And that's when the first nuclear power station actually powered a light bulb. So then the second larger experiment was in 1951 in Idaho, in the lab there. In 1954, the world's first nuclear power station generated electricity for the power grid, and that was in the Soviet Union. And then the first full-scale power station opened in England in 1956, and the first full-scale power station solely devoted to electricity production opened in the United States in 1957. And so here I have the picture of the oldest nuclear plant, which was in New Jersey from September 1968, and also the pictures from the most famous nuclear power plant that most of us are most familiar with, Springfield Nuclear Plant and the Nuclear Safety Inspector. Okay, and so there are 2 nuclear plants in Texas, and I think in the past, maybe we even tried, or I don't know if Dr. Parker organized the field trips to these nuclear plants. Yeah. One is in Bay City, and one is in Glen Rose, close to Fort Worth. Okay, and so for the remaining time, I just wanted briefly to go over some of the projects that I have been recently working with my students, which is modeling of the flow inside the pipes. That's what my research from the PhD is about. We studied, of course, from the mathematical point of view, we just studied how gas dynamics works, and in particular also fluid dynamics. And so this is now the application that we can have in the nuclear reactors, because this is a scheme, just a very simple scheme of a nuclear reactor. And we see that there are many pipes, vertical pipes, horizontal pipes, and we have liquids and gases flowing through those pipes. So what is important for a nuclear engineer is to have a control and understanding what is the flow inside these pipes so they can prevent accidents. For example, if some pipes are heating and the liquid is a very high temperature and very high pressure, they want quickly to add gas, cooling gas in those pipes so they can cool them down and prevent the accident. And so what is important to understand is at any point of time and at every pipe, what is the distribution of gas and those liquids, to know the exact temperature, exact pressure, so they have control of this pipe and the plant. And so one of the research projects I have been working on the last few years is a two-phase flow of liquids and gases in those pipes. So, so we just imagine these are horizontal pipes. So in physics, they see that there is a difference whether the pipe is horizontal or vertical, what the flow inside the pipe will be, depending on gravity and other physical regimes. And so these are some regimes in horizontal pipes. White denotes here gas and gray is liquid. But what I chose to study with my students was actually the flow in vertical pipes. There was no particular reason why we chose vertical pipes. It's just something that I have encountered first. And so in the future, we probably will consider horizontal pipes as well. And so these are just several different regimes. So the first one, the first picture here is when we have pure liquid inside the pipe. Okay, so gray is the liquid, white denotes the air. So the first one is just the pure liquid inside the pipe. The second regime here is bubble flow. So we have some small bubbles inside the pipe. The third one is where we have some bigger bubbles followed by smaller bubbles. These bigger bubbles are called Taylor bubbles. And in particular, actually with my students, we worked on this third regime. Then there is also churn flow, annual flow, mist flow. Mist flow means that the pipe is mostly filled with gas and there are some droplets flowing inside the pipe. Okay, so these are just different flow regimes that we get from physics, and each regime is different mathematically. So there are different equations describing how this mixture of gas and liquid flows inside the pipe. And so we just decided to study the third situation where we have these big bubbles followed by smaller bubbles. So what we have here again, we have a pipe, and the pipe is filled with let's say liquid, and to cool this liquid, we inject at the bottom of the pipe, at the entry of the pipe, we inject gas. So we're interested how these bubbles flow inside the pipe. And so mathematically, this is modeled by differential equations. Alpha G here denotes the fractional volume of gas. Alpha L is the fractional volume of liquid. And then we have two variables. T stands for time, X stands for the spatial coordinate. So going back to the pipe, what is X? X is the distance from the bottom of the pipe to some particular cross-section of the pipe. So if we're interested in what is happening at this cross-section, okay, that's at the distance X from the entry to the pipe and the particular time T. And so these functions alpha G and alpha L, they tell us at each cross-section how much gas and how much liquid there is. So for example, at this section of the pipe, okay, this cross-section, if this is the fixed distance X, from the entry, we see that it's mostly gas, maybe 90% of gas and 10% of liquid. But at this cross-section of the gas, it's mostly liquid and just some small bubbles. So maybe now it's, let's say 95% liquid and only 5% gas. So we are interested, what is the distribution of gas and liquid throughout the entire pipe? And that's what is given by these differential equations. Now, these equations are partial differential equations. So what you see here, we don't have those prime symbols we use in calculus because now we have two variables, time and space. But so they're a little bit more complicated, but the basic methodology, how we will solve them, is basically the same. We have to understand what is the definition of derivative, like we did in calculus 1, that definition I had with the limit. So the same thing, we go over here, what is the derivative with respect to time, what is the derivative with respect to x, and we proceed from there. That's where we start with. So the goal is to solve these equations. Typically, when we have some application problems, like this problem is really from the real world applications. It's not just some small math problem we constructed to learn some technique, but actually has a deep application. It's important in engineering. Typically, those problems are much more complicated and cannot be solved just using some simple algebra, like solve the problem in a couple of lines, like we have on the test, algebra test or calculus test. These are more involved problems. So to solve them, we have to use numerical methods. So that basically some approximation methods. And so if you are a math major or data science major, and I think even computer science majors, you'll take a class at UHD, we have a class on, you're required to take the class on numerical methods. That's where you see how you solve numerically some problems. And so some classical numerical methods for solving differential equations are called finite difference, finite volume. And these methods have been known for the last 70 years. So these are very well-known, well-used methods, really used in engineering. So a few years ago, I visited ExxonMobil. I was invited to give a research talk there because I was working on some problem related to oil reservoir simulations. And I was surprised actually that what they use is really these basic classical numerical methods for their research. Of course, those methods, even though they're basic, but the calculations are very complicated because the reservoir, it has very complicated geometry. So they're very involved calculations, but they come to these basic numerical methods. And so in the last 20 or so years, with the development of data science, we're now starting to use data science methods as well in math to solve some problems related to differential equations, and in particular, artificial neural networks. So what I'm working on with my students starting last semester, we are learning about artificial neural networks. It's a new concept for me too. So when you're doing research, you have to be willing to learn new concepts. You have to be open to new concepts. It's not only studying or using what you know, but you have to learn along the project. And there are always new things coming up. The science is developing very fast. And so we decided to study artificial neural networks and see how we can use those tools to solve these classical problems in math, like two-phase problem. And so in particular with my students this semester, we are using polynomials. In 2018, so this is a very recent research in math or in data science, because math is a very old subject. So 2018, only 2-3 years old paper, is a very recent paper on using Bernstein polynomials for neural networks. And with my students, what I plan to do is we plan to extend this to quantum Bernstein neural networks, introducing some parameters Q and H. So that's what we are working on. And then I just wanted to mention another project that several of my students worked in the past, Charles Livermore, Paul Nixon, and they really made good progress. They participated in conferences. They were studying gas dynamics. So instead of studying just studying the dynamics of liquids and gases in pipes, they studied only the dynamics of gas. So for example, the question was nuclear radiation from Fukushima affected by the direction of wind. So this is a map, and this is Japan, where the nuclear plant was. And so whether the wind affected this radiation spreads to the United States. So this is the west coast of the United States and Canada. And so how can that be described? Well, there's some very complicated equations. I will not go into details, but just show you the equations. So now these are again equations, now 4 equations. Rho denotes density, U and V are velocities, E is energy, P is pressure. So these are now 4 equations we're trying to solve. And my students actually wrote the code, classical code, and they had some results how the solution looks like. And then just a few more slides is about my particular research. So just to show you that in math, we try to simplify the problems and we try to solve them. So sometimes in math, we have to study theorems and proofs. And I know the students, they don't like when we say we have to study theorems and we have to prove them, but that's what math research is about. So going down to basics, simplifying the problem, trying to find a solution. So one of the problems that I have been working on recently is trying to find a solution. So starting from that gas dynamics equations, physical equations, we simplify them, and we have here a math problem. We're trying to find a solution in a certain part of the domain, and we use all kinds of techniques, and the proofs are very long. So like in an analysis class, sometimes the proof is a couple of lines long, and the students already complain that it's too long, too hard to understand. But really, math research, sometimes the proofs can be many, many steps, as I have here, many steps, and the papers can be 20 pages long. So we have to be patient. There is also numerical results and so on. And so just some references and acknowledgements, some of the papers I used and the acknowledgements. Of course, I'm grateful to Scholars Academy, in particular to Dr. Parker, for all the support she has been given to faculty, as well to all the students supporting them for so many years. Also, thank you to Ms. Gonzalez for attending my talk today. And then also I'm acknowledging here our grants, our joint grants in Nuclear Regulatory Commission, and also my postdoctoral advisor, Dr. Barbara Kifitz. And so thank you for your attention.
Wow.
Oh, thank you. Thank you.
Wow.
Oh, I see.
It's very complicated.
Well, but the students
There's
are
2
making,
students.
the students are making
Yeah,
really
that's
good progress.
amazing.
Yes, when we break down the problem to details, they can write their code like Rafael and Salman. I have no idea what their code is, but it gives the results. So they help me a lot. They're really experienced
Wonderful.
code writers, and it's really nice to have a mixture of data science students, math students, computer science students. So I'm really glad that you always give me students with other majors, so we are able to have interdisciplinary.
Well, yeah. Well, let's see. Fakir, do you have any questions? Janaya?
Yes, I do.
Any questions?
Yeah. So,
okay.
Can nuclear power plants be based anywhere, or can they only be based in areas with a high concentration of nuclear material like uranium or plutonium?
Yeah, so in order to power the nuclear plant, we have to have access to this radioactive material. And so depending on the amount of the radioactive material that is that can be used, that's how far the spacecraft can travel. So in advance, we can predict how deep in space it can travel.
But I think in the United States, at least, they do not have to be built near uranium sources, because we can move the uranium sources around, I believe.
That's correct. Yes, that's what I.
For example, every hospital that takes care of oncology, they're going to have a uranium source, and so they're under the same. Even though they're not producing power, they're still using it, and so they're under policies also. So
yes, and I know several of our students who are actually working in radiation therapy. I think Isaac Valdez, he's in MD Anderson.
Yes. Well, actually, he just became vice president of some new company.
Oh, okay.
And so, but that was his area, dosiometry.
Yes, we were planning to have a field trip, but last spring, but because of COVID, then we didn't organize it.
I know. Fakir, that's a great question, though. And Janaya, did you know there were 2 nuclear power plants in Texas?
I did not.
I know most undergraduates do not know. And part of our, this is actually, we've had this grant for 10 years, first 5 and then the next 5. And the first 5 was really building up knowledge that there's nuclear power sources in Texas. And in engineering technology, we actually had 3 professors who worked in nuclear power plant construction.
Oh, wow.
And nobody knew at all. Well, one has passed, but Dr. Tito helped build. He's a civil engineer. He helped build South Texas Project in Baytown.
Oh, wow. That's
so very interesting.
Yes.
Yeah. Fakir, anything?
No, I don't have any questions at this time. It was pretty good seminar. I really enjoyed it. It was very interesting.
Thank you for
very
attending.
Interesting.
Both of you, Janai and Fakir, and to you, Dr. Parker and Ms. Gonzalez. Thank you for doing
Well, thank you for giving this. And, it is amazing. I do believe that math is the door to all science. I really do believe that. But I do believe, too, that the application of the mathematical concepts helps most of society understand what is going on, right? I mean, the mathematicians, they're very pure. They have a special gift, I think, to be able to work all these problems, but to be able to apply it, it's wonderful. And I love to see that you're doing that with the nuclear. I think you could do it with almost anything, but it helps, for this concrete type of piece. So we thank you so much.
Thank you. I'm grateful to the project that I was able to. So now actually my research is all about now this nuclear reactor pipes. So I completely switched because it's so interesting.
Wow.
And there's so many new developments, and especially with data science and artificial neural networks. That's a hot topic now in math.
Wonderful. Well, we need to get you connected back to A&M because they're doing this kind of research. And that would be a very nice connection beyond the gas and oil environment. But I think that, so I'm going to strive to do that.
Okay.
We'll
thank
look
you,
at
Dr.
some of the
Parker.
people that, okay.
Thank
Well, if you don't have any other questions, anyone? Oh, thank you so much. One more
Thank
time.
you.
Thank you.
Thank you so much. Thank you. Have a good day. And I'll send you, Dr. Parker, the link of the recording.
Thanks so much.
Have a nice
All
day.
right. Thank you, ladies, for attending.
Thank you. Bye, everybody.
Have a nice day.
Thank you, you too. Bye.